Hello and welcome to a video of Underfitting explained for beginners. This is me, Hasnan Heather from AI Sciences, and let's start today's video. First of all, let's understand what is the concept of overfitting. Before overfitting, we should know what are the ultimate goals of machine learning. Machine learning aims to generalize the problems. Generalized means that machine learning model learns general parameters from training data to perform equally good on unseen data. Means we provide some data to a machine learning model, and the model learns its patterns hidden within the data, and when we give the similar data to the trained model, it performs equally good on that. But if there is the case machine learning model is not able to learn the patterns in the training data due to some reasons, if model is unable to learn, the model is known as underfitted, and the reverse case is known as overfitting, when the models learns too much about the given data but could not perform good on new data, unseen data. Let's see the figures on the slides. This central figure is the ultimate goal which we want to achieve. Here, our data was given like in a pattern of V shaped, and the dotted line is the actual understanding or the learning our model made out of the data, and this is the actual requirement what we want. But here is the interesting case which we want to discuss today. The actual underlying pattern in the data was this V-shaped curve. But due to less power in our model, it couldn't capture the actual reality, and it tries to fit in with this straight line. So this is known as underfitting. And the reverse is overfitting, when the curve exactly passes through each of the data point and learns it so well that it performs very bad on other data sets. Let's move forward and understand what is goodness of fit. Goodness of fit is that how well a model fits the given training data, but it doesn't mean it fits it too good that it couldn't be able to perform good on the unseen new data. We need model complexity according to the problem, according to the nature of the problem. There are two basic concepts in machine learning. After that, we'll be able to understand what is a good fit. So let's see them. The first one is bias. Bias is the difference between our model's prediction and the actual ground truth what should be predicted. It means that there is a let me draw some figure here. Let's say the actual underlying reality was here, and our model predicted it as here. Obviously it's wrong, but how far these 2 points are actually, this is bias. And the variance is the model's variability of prediction for a given data point. It means the model, how much a model is capable of predicting a data point at with a variability. From this, let's understand from this figure what is goodness of fit. This is error on the y-axis, and this is model's complexity on the x-axis. If the model's complexity is very low, obviously the complexity is low, the model's capacity to learn is very low, and the error will be very much higher here. And obviously when we increase the model's capacity, its power of learning increases, and it learns it very well, and the loss obviously should be very less. but we have to stop in between somewhere. If the model's complexity is low, the bias is high. Bias is high means the error is high, and as we move towards higher complexity models, the bias start coming down, and the variance, which is shown here in green, starts increasing. So the simple understanding of underfitting is, we have, let me write it here, underfit is equal to high bias and low variance. The bias is high, the variance is low, we are at the position of underfit. But at the reverse case, if the variance is high and the bias is low, we are at the overfitting. But here's our point, that we need some balanced values of bias and variance for which we get the optimal results. This is the black line is actually the validation error, and the validation error starts reducing, and after a specific point where we achieve the balance between bias and variance, after that the validation error starts increasing again. So what we want a balanced complexity of a model, a point where we achieve the exact fitting of the training data. Let's see a couple of examples of regression and classification. Regression and classifications are actually the two sub problems of supervised machine learning. Supervised learning. And in classification is a discrete problem where we assign each instance a specific category, a specific class. But the regression is a continuous problem where we need to achieve some curve or some series of numbers. So let's start with discussing the good solution, where here the green line is actually representing the actual underlying reality, and the red one is what we understood out of it. So we can see for this figure, for m is equal to 3, our fitted model and the actual reality are very close. But if the model's complexity is very low, means the m is equal to 1 and the number of parameters are only 1 here, the model was not able to learn the reality, and it just gave a straight line which couldn't capture anything. And here is the case of overfitting. Similar is the case with classification problem, where two classes were separated, and due to noise they were into each other. And the good fit was when our model learned a curve, such a curve which most of the instances are separated very good. But if the model's ability is very low, it couldn't be able to capture the reality, and it wouldn't be able to separate these two classes very good. How do we get that underfitting has happened? So there is a simple right hand thumb and rule which will tell us that underfitting has happened or not. If the results on training data as well as on testing data are very bad, if a model is performing very bad, equally bad on both of the data sets, means training data and testing data, it means there is a situation of underfitting. For example, we perform some classification and we got 30.9% accuracy on training data and the close accuracy on testing data. So this is now let's understand why underfitting happens. When the bias is high and the variance is low, as we talked earlier. The bias is high and the variance is low, overfitting happened. When the number of parameters are very less in a model, means the ability to learn is very less, the underfitting will happen definitely. When the training is not completed, means a model needs some specific time or number of iterations to train itself over our training data. But if we do not provide it enough training time, the training will be less and the model won't be able to capture the whole ground truth of the whole reality of the data, and a model will be overfitted. Insufficient training data. If we have a very complex model, uh, for this, if we have a very complex model, but we have very less data sets. Our data set contains very less points. So model is not able to learn its all of the parameters from this smaller data set. The smaller data set does not have ability to completely define the problem. So if we want to avoid underfitting, we need more data. Insufficient complexity of the model. If the model is not that much compatible, no matter how good or how much data we provide, the data sets, let's say, very large, but the model is very linear and very weak. So our model won't be able to learn the variances and patterns within the data set, and model will be underfitted. Now let's see some code example where underfitting is happening. Okay, we first imported our important libraries, and then we generate a sample data out of a function and with a general randomness, and we plot the data. The data looks like this in the figure. We split the data into training and testing sets. Here 80% training and 20% for the testing set, testing purposes. Then we choose the polyfit. It's a function in NumPy which fits the polynomial on the data. Here we made a function to use this function and to display the results. So let's see couple of results of polyfit. When we provide the very basic, a very smaller number of parameters to the polyfit, means only 1 degree polynomial will be fitted to the data. 1 degree polynomial only able to draw a straight line, and straight line could not fit this data. By the way, here blue data points are training set and the yellow data points are from testing set. So low order polynomial are not able to fit properly. Then we increase the power of the model, and it actually performed a bit better than the previous one. And we increase the power of the model, and again data is not fitted correctly, and then we reach to the optimal solution. When we used 4 degree polynomials, it fitted exactly the training data as well as the testing data, so it performed very good. But if we keep on increasing the model's power, means the number of parameters, then there will be a time when overfitting happens. Our training data is fitted very perfectly, but the training data, the curves deviate from to the other side. And same is the case if we keep on increasing the power. Here is an interesting figure of root mean square error, which is actually showing some important results. Here with the blue line is for the training and the yellow line is for the testing, by the way. In start, the error of the training and testing both were very high, but with the increase in polynomial degree, they start decreasing. At a point of polynomial degree 4, they were almost equivalent, and it is the area where we get the perfect fit. If we keep on increasing the power of the model, then the training error starts decreasing or it stays the same, but the testing error again starts increasing. So we need a good complexity of the model where we get the good results on training and testing data as well. I hope you enjoyed the video. Please like our video, subscribe our channel, and please visit us on the links shown on the screen.